Good morning, class. Before us, we are going to study about Form 1 work, chemistry, and our topic for today is air and combustion. For us, we have 9 group members, and the first one we have Austin Ocheng, Chepngetich Salome, Judith Cherop, Nyakoi Frida, Brian Ongondi, Corey Richard, Valentine Masika, Lois Agutu, and finally we have Simiu Daniel. These are the members who are going to tell us more about air and combustion. And I'm going to take the introduction part. I'm Chepngetich Salome. Okay, I'm going to talk about air. We all know that air is a mixture of gases which makes up the Earth's atmosphere, and these gases are colorless and odorless, and hence we can't see them, but we can only feel them. The atmosphere is an ocean of these gases which consist of nitrogen, oxygen, carbon dioxide, and inert gases. So now we need to know about the uses of air. With the first one, you have it sustains lives and growth. The second, we have combustion. The third, we have maintaining temperature, supply of energy, and photosynthesis. For us as human beings and animals, we should know that we breathe in oxygen and breathe out carbon dioxide, which is used by plants for photosynthesis. So air sustains life on Earth. Living organisms need air for respiration. Plants also need air for photosynthesis. We've said that human beings take in oxygen and breathe out carbon dioxide, which is used by plants. Air is required for combustion of fuels to give energy. When we burn oxygen, we get a type of gases which we can use for combustion of fuels to give energy. So we need to know more about air and its uses. Even as we continue with this topic, we need to know about the different kinds of air we have. As we've said, we have oxygen, we have carbon dioxide, nitrogen, and also inert gases. Let me welcome the next presenter who is going to take us through oxygen used in combustion, who is Daniel Simiyu. Welcome, Daniel.
Okay, thank you for the warm welcome. I want to go through the oxygen used in combustion. Of course, I'm Daniel Simiyu. I want to talk about oxygen used in combustion. So we have been told that air contains different gases with their percentage composition. That is, if we first started with nitrogen, we're having a percentage composition of 78.1 degrees, 71.8. Then we had oxygen having a percentage of 20.9%, carbon dioxide having a percentage of 0.03%, and have rare gases having a percentage of 0.97%. So talking about oxygen, we want to see basically the percentage of air that supports combustion, and we'll be carrying out an experiment. That experiment will be requiring us to, it being an experiment, we have a procedure. So the procedure is, first you start by putting dilute sodium hydroxide solution in a trough. Then you place a small candle on a cork and float it on the solution. Then you cover it with a gas jar. You mark on the gas jar the level of the solution. Then you measure the height of the air column and record it. Then you remove the jar and you light the candle. You gently cover the burning candle with the gas jar. After the candle has gone off, you leave the apparatus to cool to room temperature. Then you mark on the gas jar the final level of the solution, and then you measure and record the height of the air column once more. After that, you remove the gas jar and measure the change in height. So this is basically the figure that concerning that experiment. We are seeing that we started with a candle and a cork. Then we have a solution with sodium hydroxide solution, and we measure the initial height of the gas jar. Then we lit our candle, that is part B. As you are seeing, the candle is lit now and we're covering it. Then part C, you are seeing that the candle has gone off. So, and we are seeing that the level of sodium hydroxide solution is also reducing in the trough, but increasing in the air, in the gas jar. So we want to ask ourselves some few questions. Why did the candle go off, and what happened? Why did the level of the solution of sodium hydroxide rise in the gas jar and the level of sodium hydroxide drop in the trough? So what could be some of the reasons? The reason is because the candle went off because it used the active part of air, which is fixed in the enclosed gas jar. So you are seeing that when we took our gas jar, we covered the burning candle, so there was some air that was enclosed in that gas jar. So you are seeing that part of air, as you know, air contains different gases. So the active part of air, which is basically oxygen, is the one that was used for that candle to burn. So after the candle has used all the oxygen that was in the gas jar, the candle went off. So that is the reason why the candle goes off, because it has already used the oxygen, the active part of air. So we'll be calculating the percentage composition of that active part of air that helped the candle to go off. So another question that we asked ourselves was, why does the level of the sodium hydroxide solution rise in the gas jar and reduce in the trough? So the basic reason is because that when a candle we know is made up of carbon. So when we expose carbon to oxygen, or when we burn carbon, we produce carbon dioxide gas. So the carbon dioxide gas is the one that was, now after the oxygen has been used, the carbon dioxide was released in the gas jar that filled the gas jar. And so the presence of sodium hydroxide solution was able to absorb the carbon dioxide gas that was found in the gas jar. So that part of air, that was being occupied by carbon dioxide, we see that the sodium hydroxide solution absorbed that gas. So that is the reason why the level of the solution is increasing in the gas jar and reducing in the trough. So another reason is because of the greater atmospheric pressure acting on the surface of sodium hydroxide solution, forcing the solution up in the jar. So we want to see some sample results. So these are the sample results of that experiment. The experiment is believed to have been carried out. So we are talking about the theory part of that experiment. So basically we'll be doing it in the laboratory in our next double class, but for today we'll be just looking at the summary. So when we started our experiment, we saw that the height of the column before burning was 16.0 centimeter, and after burning we also measured the height, which was found to be 12.9 centimeter. So to get the height of the air that is used, we are taking now 16.0 centimeter. We are subtracting from 12.9 centimeter, getting 3.1 centimeter. So this is the height of the air that is used. So when we want to calculate the percentage of the active part of air, we are saying that we are taking the height of the air that is used divided by the initial height of air, then we are multiplying with 100% to get a percentage. So when we calculate, we get 19.275%. So this is the experimental value, but in our theoretical part, when we were being told about the composition of air, we were told that oxygen, which is the active part, should occupy a percentage of 20%. So what could be the possible reasons why we are not getting the accurate 20.0 degrees 20.0%, and in our experiment we are getting 19.275%. So what could be some of the errors that we encountered? So some of the errors could be, you can say that maybe when the candle was being burned, not all the oxygen was used. Not all the oxygen was used. Another reason that where the error may have come from is, maybe we can say that the carbon dioxide gas that was produced after the candle has burned, maybe it was not absorbed fully with the sodium hydroxide solution. So that is the reason why we are not getting 20.1%. So that will be my end of the presentation. I will be welcoming another presenter to take us through the combustion part of air. So that will be Lois Agutu. Welcome, Lois.
Thank you. I'm Lois and I'm going to talk about combustion. So starting with the definition, combustion, also referred to as burning, is a process in which a substance combines with oxygen with the production of heat. And next, we are told that the part of air that supports combustion is active air. So as we are discussed before, we said air is made up of several components, and one of them is oxygen, and then we have carbon dioxide, we have nitrogen, and the noble gases. So not all the air is used during combustion, and the active part, we said, forms around 20%, and that is oxygen. So like said by the first presenter, air has many uses, and one of the uses is burning. So our previous presenter took us through an experiment where we are supposed to determine the volume of oxygen used during burning. And so I'm going to take us through the second experiment that involves burning copper to determine the volume of oxygen also used during combustion. So in this experiment, we are going to pack copper tannings in a long hard glass tube. Then we are going to connect the tube with two glass syringes. So we have that experiment on your textbook. You look at it on page 96. So after heating the copper tannings, they'll turn red hot. We are going to pass air from syringe A slowly through syringe B. So we are going to do that repeatedly around several times until the copper tannings turn black. So before that, we are going to record the volume. So we are going to record the volume of air in syringe B before passing copper 2. And then after that, we are going to allow the glass tube to cool, and then we are also going to record the volume of the gas after burning. So we know copper is a red-brown metal, and when it's heated in air, it will turn black. And the turning black is as a result of burning it through oxygen to form copper dioxide solid. So after recording the volume of air in syringe A before heating and the volume in syringe A after heating, we are going to calculate the volume of air used up during heating. So to get the percentage of the volume used during burning, we are going to take the volume used during heating divided by the original volume of air before each heating multiplied by 100. So in this experiment, we find that the percentage used during burning is exactly 20%, as should be, and about 80% of air is left and does not react with heated copper. So this reason is because the 80% left is known as the inactive air. And we had said before, only the active part of air is used during burning. So in the experiment, we note that we used the glasswood plug, and the significance was to stop the copper tannings from being sucked into the syringe. We also emphasized that the air should be passed repeatedly over the heated copper to ensure that all the oxygen in the syringes and the tube has been used up. So the air is also passed slowly to allow enough time of contact between the reactants. And finally, the gas left in the syringe does not react with copper because it is mainly nitrogen. So the possible sources of error in this experiment include the air initially present in the tube is not accounted for. Secondly, there is possible leakage of air. And thirdly, not all the oxygen may have been used up. So we know that while we are conducting these experiments, we cannot always get exactly 20% of air, as we had mentioned. So our previous presenter also noted when he was discussing the experiment where we had heated a candle passed through sodium hydroxide. So we said that some of the errors would be because not all the oxygen had been used up during burning, and the sodium hydroxide solution used may not have absorbed all the carbon dioxide, and then we could also have a buildup of carbon dioxide levels. So to make sure that such errors are reduced so that we get our exact values, as I had mentioned before, that is 20%, we'll make sure that the conditions used during the experiment had followed, and I had mentioned before we used a glass wool, and then that was to prevent the copper tannins from being sucked into the syringes. We also made sure that the air was passed repeatedly over the heated copper tannins. So this was to ensure that all the oxygen were used up. Then we also made sure that we did that slowly to allow enough time for the reactants. So when we do this without limiting ourselves, and we'll make sure that the errors are limited, when we do our calculations, we'll find that the volume of air is exactly 20%. So that proves our point that the active part of air used during burning or combustion is 20%. So I'm going to welcome our next presenter to talk about rusting. Welcome, Brian.
We are going to talk about rusting. Corrosion of iron is called rusting. Corrosion of other metals is referred to as rusting. However, you ever known why old iron nails or sheets look different from new ones? Old iron sheets are brown and dull, while new ones are shiny. Many other metals change after some time due to some chemical reactions which take place on their surface. Then below we have a figure whereby we are going to test for the conditions of rusting. We have 5 test tubes, in which tube 1 we have tap water and nails, tube 2 oil, boiled water and nails, tube 3 anhydrous calcium chloride, cotton wool and nails, tube 4 salt water, nails, and tube 5 on nails. Whereby it is now observed that the nails in tube 1 would have rusted after 3 days. Then the nails in tube 5 would have rusted to a small extent. The rusting in tube 4 is more intense. Then finally no rusting is observed in tube 2 and 3. For tap water contains dissolved oxygen. The iron nails combine with oxygen in the presence of water to form hydrated iron oxide. Then there is a reaction between iron and oxygen which forms iron 3 oxide. Then iron 3 oxide reacts with water to form hydrated iron 3 oxide, which is brown. Therefore, rusting occurs in tube 1 because both water and oxygen were present. Some rusting occurred in tube 5 since there was some moisture in the air. Rusting was more intense in tube 4 due to presence of dissolved sodium chloride. Then, when water was boiled, all the dissolved gases in it were expelled. The layer of oil covering the boiled water prevented re-entry of air. This is oxygen. There was no oxygen in tube 2, and there the nails did not rust. Anhydrous calcium chloride absorbs moisture from the air. Thus, air in tube 3 is dry. It was necessary to caulk tube 3 to prevent entry of water vapor from the atmosphere. The nails in tube 3 do not rust because there was no water in it. The presence of water and oxygen are necessary for iron to rust. Rusting occurs faster in salt or acidic surroundings. For example, cars rust faster in Mombasa than Nairobi. Therefore, as we continue, the corrosion of iron due to this reaction with atmospheric oxygen and moisture is called rusting. Then rust forms a brown coating on the surface of iron material because rust is porous. Once an object starts to rust, the process continues until the object is completely destroyed. These reactions are referred to as corrosion. I'm going to welcome the next presenter to talk about the conditions of rusting. Judith Cherop. Welcome.
Okay, thank you. I'm Judith. I'll be taking you through conditions for rusting to occur. The presence of water and oxygen are thus necessary for iron to rust. Rusting occurs faster in salty or acidic conditions. For example, cars rust faster in Mombasa than in Nairobi. Tap water contains dissolved oxygen. The iron nails combine with oxygen in the presence of water to form hydrated iron oxide. Iron will combine with oxygen to form iron 3 oxide. Iron 3 oxide will combine with water to form hydrated iron 3 oxide, which is brown in color. Allow me to welcome the next presenter to take us through methods of rusting, methods of preventing rusting. Welcome, Masika Valentine.
I'm going to take you through methods of preventing rusting. Rusting destroys machinery, equipment, and roofs made of iron. The basis of rust prevention is to keep iron out of direct contact with water and oxygen. The following methods are widely used to prevent rusting of iron. The first one is painting, e.g. cars and roofs. Then the next is coating with other metals. This can be done through galvanization. Then we are going to talk about alloying. This involves the mixing of iron with one or more metals to produce a substance which does not rust. The next point is oiling and greasing. This is the method used in moving engine parts where other methods cannot be used due to friction. And the last point is sacrificial protection. In this arrangement,
A more reactive metal such as zinc or magnesium is attached to the ion structure. The more reactive metal corrodes instead of iron. This method is applied in ships and water and oil pipes. I would now like to welcome the next presenter to present about oxygen, Frida Nyakoe. Welcome.
I'm Nyakoe. I'm going to take you through the part of oxygen. As we see, oxygen exists freely in the atmosphere as a gas. Its chemical symbol is O, and when two atoms of oxygen combine, they form a molecule with a chemical formula of O2. Oxygen is also found combined with other elements such as hydrogen in water and metal in metal oxides. It is the most active component in air. And this is the lab preparation of oxygen using this video.
Preparation of oxygen using hydrogen peroxide. Hydrogen peroxide is a colorless, heavy, strongly oxidizing liquid. Its chemical formula is H2O2. It is highly unstable. It is used in the preparation of oxygen gas in the laboratory. Set up the apparatus as shown here. Some manganese dioxide and water is taken in a conical flask. Hydrogen peroxide is added dropwise through the thistle funnel. You will see that the oxygen gas comes out through the delivery tube. Oxygen gas is collected by the downward displacement of water.
The preparation of oxygen is set using these following apparatus. We have flask, dropping funnel, gas jar, water, and trough. Here 2 grams of manganese is put in the flask and hydrogen peroxide is added dropwise. And oxygen is collected using downward delivery because it is less dense than air. Peroxide decomposes slowly to produce oxygen and water under normal conditions. On adding manganese 4 oxide, the rate of decomposition is speeded up, and manganese 4 oxide acts as a catalyst. A catalyst is a substance that alters the rate of a reaction. Manganese 4 oxide is used as a catalyst in the decomposition of hydrogen peroxide. Oxygen relights a glowing sprint, and this is the test for oxygen. Oxygen can be prepared also by adding water to solid sodium peroxide, and the equation is sodium peroxide plus water to produce sodium hydroxide plus oxygen. And another one is heating potassium permanganate. On heating potassium permanganate, it produces potassium plus manganate 4 oxide plus oxygen, and that is the part of oxygen. Now I welcome the next presenter to present on burning metal in oxygen.
Thank you, Frida, for welcoming. I'll be taking you through burning metals in oxygen, and we've known how oxygen is being prepared in the laboratory using the manganese oxide and the other one which has been shown in the video as well. Now, burning metals in oxygen, that is what I want to discuss, and those are the notes. Now, from the slides, many metals burn in air and in oxygen at different rates. They burn faster in oxygen than in air. Nitrogen is the component of air that slows down the rate of burning. While metal burns in oxygen, they form metal oxide. Now, there is a difference between burning in oxygen and burning in air. You might think that the two terms are the same, but generally they are not. Now, there is a difference there, and the difference is if you burn something in oxygen, it forms, you burn, actually it involves lighting and lighting that let's take an example of a metal. Burning it in oxygen means you are burning it with a light form, but burning it in air is somehow different, since burning in air, you just like the exposure, you expose it on air. So if you burn a metal in oxygen, actually you will form a metal oxide. If you burn a metal in oxygen, you get a metal oxide. Example is a sodium. If one burns sodium in oxygen, you form a sodium oxide. Another one is calcium oxide. Those are the metals. If you burn a calcium metal, you burn it with oxygen, then you form a calcium oxide. The same reactions as well occurs when you burn a magnesium in oxygen to form magnesium oxide. So therefore we say sodium reacts most vigorously with oxygen, while copper is the least reactive. The reason why we say so is yet to tell you, but before that, let me show you how oxygen reacts with sodium in that case. Let me play a video to show the same. So that is the reaction of sodium with the oxygen. Sodium is a group 1 metal.
If we heat a sample of sodium metal, we see that it melts rapidly. Sodium has a lower melting point than lithium. The sodium starts to react with the oxygen in the air and burns. If we let a little bit of the smoke be drawn into the burner, we see the brilliant yellow color of the sodium flame test. The white smoke that we see is actually sodium peroxide being formed.
So from the video, we are able to see that oxygen burns in air very vigorously, producing a yellow-orange flame. If you are very keen, you saw a yellow-orange flame. Now, after the burning, the appearance of the product was a white. Now, the product that is formed, that is sodium oxide. So that was a reaction of how sodium react in oxygen. But now, how does sodium react in air? Sodium reacts in air burns in air to form few sparks with a yellow-orange flame as well. You get the difference? Hope I'm not confusing. Now, apart from sodium, calcium as well burns in air vigorously with a red flame. You have to differentiate the types of flames produced when different metals burns in oxygen. The same thing, when magnesium burns in oxygen, then it burns brightly with a white glaring flame. In our lab, I'll show you how magnesium burns. You will actually see the glaring flame. Another metal we can talk about is iron. Now, iron also reacts, burns in oxygen brightly with a sparks. It glows. In fact, it does not burn, it glows with the brightly and sparks, producing some bright and sparks. Now, assignment that I want you to go and confirm, you can go and read it from your notes, or or whichever source, is to go and see how copper burns in air, at the same time how copper burns in oxygen, producing which types of flame. You will do that. Then the appearance of the products. Now, reactive metals, another point to note, reactive metals such as sodium, calcium, magnesium react with nitrogen in the air to form nitrides. Now, the nitrides formed by the metals when they react with nitrogen reacts with water as well to form respective hydroxide plus ammonia, respective metal hydroxide plus ammonia. Now, the reaction which elements combine with oxygen are referred to oxidation. You will be asked, what is oxidation? Oxidation refers to the process or the reaction in which elements combine with oxygen. That is what we call oxidation. Now, the substances to which oxygen is added is said to have been oxidized. Now, that is the substance to which oxygen is added. That is substance. That is the substance to which oxygen is added is said to have been oxidized. Now, the metals can be arranged in order of their rates of reaction with oxygen, from the most reactive to the least reactive. Now, this arrangement is what we referred to as a reactivity series of metals. Mercury, silver, and gold are less reactive than copper and not easily oxidized. Hope we are following. Is there anyone who is not following? Now, in the reactivity series that I've just stated, potassium is the most reactive metal, followed by sodium, calcium, magnesium, zinc, in that order, up to the gold, where gold is the least reactive. So that is the summary of how different metals burns in oxygen. Now, another point to put in cautious point is that products of burning sulfur and phosphorus are poisonous, and therefore experiments should be done in a fume cupboard. Phosphorus is also highly flammable. I'll show you that in our next class, practical part. Thank you. Allow me welcome the next presenter, who will be taking us through the uses of oxygen, and that next presenter is Corey Richard. Corey Richard, welcome.
Thank you so much, my brother, for the welcome. I'm Corey Richard. So I will be taking you through the uses of oxygen. So, as we have been introduced by our previous presenters as oxygen gas, so we have various uses of oxygen. So, number one, I may say that oxygen is used by living beings or living things in respiration, and we know that respiration is the process by which chemical substances are being broken down to release energy. Another use of oxygen is that oxygen is being used in water treatment and chemical combustion. Also, oxygen, another point is that air enriched with oxygen is used in hospitals by patients with breathing difficulties. Another point is that when this oxygen is being mixed with helium, it is used by mountain climbers and deep sea divers. Another point is that oxygen is used to burn fuels such as those used in propelling rockets. Also, a mixture of oxygen and acetylene burns to produce a very hot flame used in welding and for cutting metals. It means that when acetylene is mixed with this oxygen, it burns in a very high temperature to melt the metals. Also, during steel making, oxygen is used to remove iron impurities. So we know that in preparations of steel, oxygen is being used to remove impurities. And that brings me to the end of my presentation and also the end of our presentation. Thank you all.